Thank you for taking the time to join today. The focus of this session is ransomware resilient backups, specifically in Veeam environments, and how architecture determines whether recovery actually works when it matters. We'll be using StoneFly as the reference architecture throughout this session, not so much as a sales pitch, but as a practical example of how immutability, isolation, and true air gap can be implemented together. The intent isn't to deep dive product features. It's to clearly explain why these controls matter, how they fit together, and what to look for when evaluating your own backup design. By the end of this session, you should be able to look at your environment and answer one question with confidence. If we're hit tomorrow, do our backups actually survive? So let's get started. Why do backups still fail? You'll notice the first point says backups usually exist. And that's important because most organizations do have backup infrastructure in place. The failure happens at the second point. Backups are deleted first. Attackers deliberately target backup repositories before they encrypt anything, which leads directly to the third point. Recovery fails before encryption. By the time files are locked, the ability to recover is already gone. This is the pattern that we see over and over again. This slide introduces the three controls that actually determine whether recovery is possible: isolation, immutability, and air gap. Immutability means that once backup data is written, it cannot be modified or deleted, even by administrators. In StoneFly, this is enforced using mechanisms like object lock, worm-style vaults, and immutable snapshots. If credentials are compromised, the data still survives. Isolation means the system is still connected, but access is tightly controlled. There is a network path, but it's mediated and enforced by the StoneFly appliance, not by Windows or the general network. Veeam can see the repository, but it cannot freely access it. Air gap means there is no usable path at all. No SMB, no iSCSI, no S3 endpoint, no routable network connection. With StoneFly, air-gapped repositories simply do not exist on the network until they are intentionally activated. The simplest way to remember the difference is this: immutability prevents deletion, isolation limits access, and air gap removes reachability entirely. StoneFly supports all three, and that's why backups survive even when everything else is compromised. This slide describes the most common Veeam deployment we see in the field. In most environments, Veeam runs on a window-based server. It's domain-joined, network-facing, and treated like any other infrastructure server. Backup repositories are then exposed using standard protocols, SMB, NFS, or iSCSI, because that's how Windows and Veeam are designed to interact with storage. The critical point is the last line. Admin credentials equal full access. If an attacker compromises domain admin or local admin credentials, they don't need to break Veeam. They already have permission to access the backup server and the storage it controls. That's why traditional architectures fail. The backup environment is exposed to the same threats as production systems. Let's talk about the StoneFly design principle and the separation of responsibility. The first point is important. Veeam runs the backup logic. That includes orchestration, scheduling, deduplication, and recovery workflows. None of that changes. What StoneFly changes is the second point. Who controls access to the storage? Instead of the backup repository being directly exposed to Windows or the network, StoneFly introduces an independent appliance that mediates all access. Veeam can write backups, but it does so under strict control through policies, enforcement, and purpose-built storage logic. That leads to the final point. Storage is not openly network facing. There are no generic file shares or block devices sitting exposed on the LAN. This is the separation of concerns. The backup orchestration stays flexible, but the storage becomes fortress grade. Up to this point, we've talked about what works, immutability, isolation, and air gap, and how StoneFly separates storage from the backup engine. StoneFly implements these protections in layers so that if one control is bypassed, the next one still holds. And layer 1 is immutability. As the slide says, this is write once, delete never. Once backup data is written, it cannot be modified or deleted even if administrator credentials are compromised. StoneFly enforces immutability using multiple mechanisms, not a single setting. The first is S3 object lock, implemented on-premise using S3 compatible storage with retention enforced at the storage layer. The second is worm-style vaults, which provide hardware-enforced write-once protection for long-term retention and compliance. The third is immutable snapshots, which create protected point-in-time copies that cannot be altered, allowing rapid rollback to a known good state. The key takeaway is this: immutability is not a feature you turn on. It's a condition that survives credential compromise. Layer 2 builds on immutability by removing reachability altogether. Immutability assumes that attacker may still be able to see the data but can't delete it. Air gap assumes something worse, that eventually everything connected will be compromised. That's why the second layer is air gap. As the first point in the slide states, these are isolated repositories. They are physically or logically separate storage pools with no persistent connectivity. The second point is critical. No SMB, no iSCSI, no direct access. Traditional network protocols are disabled, and there's nothing for an attacker to authenticate or exploit. The third point explains how this works operationally. Write once, then isolate. The network path exists only during a controlled backup window. Once the backup completes, that path is removed. At that point, we're no longer relying on permissions or controls. The network path itself is gone. That's what makes a true air gap. Layer 3 is controller isolation. And this is where StoneFly goes beyond what most environments require. At this layer, StoneFly introduces a separate air-gapped controller with its own management plane, isolated from both production systems and the Veeam server. In some deployments, this controller can also run on separate physical hardware, and when it's not in use, it can be physically powered off. At that point, the hardware itself is offline. The controller is activated only through policy-based rules, determining when it's allowed to connect or receive data. Outside of these windows, it remains offline and unreachable. This creates true defense in depth. Even if production and backup systems are compromised, the isolated controller remains out of reach. Most companies don't need this level of isolation, but for highly regulated or high-value environments, it provides an additional layer of certainty. This slide brings the three layers together in a real-world scenario. First, production systems are compromised. Files are encrypted, systems are locked, and operations are disrupted. Next, the backup server is compromised. Attackers gain access to the Veeam infrastructure, steal credentials, and attempt to delete the backups. This is where the difference shows up. Immutable copies survive. Layer 1 prevents deletion. Air-gapped copies are unreachable. Layer 2 removed the network path. And if deployed, the isolated controller remains offline. Layer 3 removes even the management plane. The result is that attackers can compromise almost everything except the backups that matter. At that point, recovery is no longer a question of if, but how quickly. Up to this point, we've focused on making sure backups survive an attack. This slide is about what happens after that. Because this is a Veeam-ready platform, all of Veeam's recovery capabilities remain available. That includes instant VM recovery, file level restores, and full application recovery directly from protected repositories. The second point is DR and sandbox testing. Because the backups are isolated and immutable, they can be safely mounted into sandbox or test environments. That allows recovery testing, patch testing, or validation without touching production or live backup infrastructure. The final point is scale. This architecture is not limited to a single box or a fixed size. It scales from small environments measured in terabytes to enterprise deployments measured in petabytes without redesigning the protection model. The key message here is simple. Strong protection does not come at the expense of recovery speed or operational flexibility. This slide brings everything together for the core takeaway. Veeam handles the recovery logic. It remains the orchestration engine, managing backups, restores, deduplication, and recovery workflows. StoneFly ensures survivability. Through immutability, isolation, and air-gap, backups are protected in ways that survive credential compromise and network attacks. And that leads to the final point. If backups survive, ransomware fails. Ransomware only works when recovery is impossible. When backups are protected and recoverable, attackers lose leverage and the incident becomes an operational problem, not a business-ending event. The formula at the bottom says it all. Protected backups plus proven recovery equals ransomware resilience. And that's the outcome we're all aiming for. Thank you again for taking the time to join today. If you'd like to explore this architecture in more detail, we're happy to continue the conversation, whether that's reviewing your current design, discussing use cases, or walking through how this would apply in your environment. My contact details are on the screen. Please feel free to reach out directly after the session, and thanks again. I'm happy to take any questions.